Hey everyone, and welcome back to the Deep Dive. You know the drill. You're here because you're all about getting to the heart of things, and honestly, who's got time to wade through endless explanations? Today we're diving headfirst into the world of polynomials.
Polynomials, yeah.
Now, I know. For some of you, that word might bring back some uh, not-so-fond memories of high school math class, but trust me, stick with us.
It's going to be worth it.
We've gone through our sources, and we've got some really good ones this time, and we're going to break down those core concepts and all the important terminology, focusing specifically on polynomials with just one variable.
Right, the building blocks.
And, maybe you're thinking, okay, polynomials, that's great, but what's the big deal? Well, get this. They're actually way more than just some abstract mathematical idea.
Oh yeah, they're everywhere, if I know where to look.
I mean, think about the smooth curves of a bridge, or the way a roller coaster twists and turns, or even those incredible realistic graphics in video games. A lot of that, behind the scenes, is powered by the magic of polynomials.
It's true, they're like the hidden language of shapes and patterns.
So, ready to unlock the code?
Let's do it.
Perfect. Our sources kick things off by talking about, well, just kind of set the stage with algebraic expressions in general. So an algebraic expression, it's basically like a sentence in math, right? It uses numbers, variables, our good friend x, maybe ey here and there, and operations like adding, subtracting, multiplying, even dividing sometimes.
Right, the basic toolkit.
Now, a polynomial in one variable, it's a particular type of algebraic expression. It's got a very specific form. And our source actually lays it out. It's an xn plus a or plus a1x plus a0. Now, that might look a little intimidating.
It's a mouthful, yeah.
But the key thing to remember here is that all those exponents on our variable, those little numbers up top, they got to be whole numbers. That means 0, 1, 2, 3, so on.
Yeah, none of those fractions are negative numbers. That's what makes it a polynomial.
Exactly. And our sources give us some great examples of what are polynomials. So something like 2x, that's simple enough. Then we've got x squared plus 2x, a bit more complex. And then they go to x cubed minus x squared plus 4x plus 7. You can see they're getting longer, right?
They can get pretty involved.
But even then, the exponents on the variables are still whole numbers, 1, 2, or 3 in this case. And it doesn't have to be x either. Our sources use other variables too, like 3y squared plus 5y or t squared plus 4. Still polynomials.
As long as those exponents are whole numbers, you're good to go.
Now, you know what they say. Sometimes the best way to understand what something is to see what it isn't.
Right, look at the flip side.
Our source throws in some examples of algebraic expressions that don't quite fit the polynomial bill, like they have x plus 1x. Seems innocent enough, but remember, 1x, that's the same as x to the power of -1 and -1.
Not a whole number. No polynomial.
Exactly. Another one, 3x plus the square root of y. Now, the square root of y, that could be written as y to the power of 1/2. And again, 1/2.
Not a whole number. Not a polynomial.
Boom. They give us another tricky one, too. 3 divided by the square root of y plus y squared. That first part, 3 over the square root of y, well, that involves y to the power of -12. Not a whole number, right?
Definitely not. So, again, not a polynomial.
So you see, looking at those examples that don't work, it really helps to clarify what a polynomial actually is. It all comes down to those exponents.
Yeah, those exponents got to be whole numbers. That's the key.
Okay, so now we've got a pretty good grasp of what makes a polynomial. Let's dig into some of the vocab, those specific words that mathematicians love to use.
Got to know the lingo.
So first up, terms. Polynomials are essentially sums of these things called terms. For example, if you have an expression like modulus x cubed plus 4x squared plus 7 by 2, each of those pieces separated by the plus or minus signs is a term. So we've got -x cubed, then 4x squared, then 7x, and finally -2, all terms.
And each of those terms has something called a coefficient. That's just the number that's multiplied by the variable.
Like the number out front.
Exactly. So in our example, negative cubed plus 4x squared plus 7 by 2, the coefficient of x cubed is -1. The coefficient of x squared is 4. The coefficient of x is 7. And that last term, -2, well, that's the coefficient of x to the power of 0 because, well, anything to the power of 0 is 1.
Oh, that's right.
Except for 0 itself, of course. That one's a bit special.
Always a global case. And our source, to really make sure we get this, they ask a question. They say, do you know the coefficient of x and x squared x plus 7? What do you think?
Let's see. That's the number right in front of the x.
Yep.
So in this case, it's -1. Got to keep that minus sign in mind.
So important. Now, here's a fun fact. Even plain old numbers like 2, -5, 7, they're actually considered polynomials, too. They're called constant polynomials.
It's true. You can think of 2 as 2 times x to the power of 0. Fits the definition perfectly.
Sneaky, right? And there's one very special constant polynomial, and that's 0. It's called a zero polynomial. It has some unique properties, particularly when you get into more advanced stuff, but we won't get into that today.
We'll save that for another deep dive.
Exactly. So we've got the parts, terms, and coefficients. Now let's talk about how we can actually categorize these polynomials, put them in different groups.
Right. Organize them a bit.
So one way to classify polynomials is based on the number of terms they have. If you have a polynomial with just one term, like 2x or just 2 or maybe 5x cubed, even negative 5x squared, or y or u to the power of 4, all of those are called monomials.
Mono meaning one.
One term, easy enough. Then we got binomials. Those are polynomials with exactly two terms, like x plus 1 or x squared minus x y to the 9th power plus 1, or u to the 15th power minus u squared.
Bi meaning two terms.
You got it. And then if you have three terms, we call it a trinomial. Examples include things like x plus x squared plus pi. That one always throws people off.
Yeah, pi, that's just a constant. It's fine.
Exactly, it's just a number. And then we have 2 plus xx squared, u plus u squared 2, and y to the 4th power plus y plus 5. Those are all trinomials.
Tri, you guessed it, means three.
Three terms. Okay, so we've got the basic parts down terms and their coefficients, and we know how to categorize them by how many terms they have. But there's another important characteristic of polynomials, and that's their degree.
Degree, yeah, that's a big one.
The degree of a polynomial is simply the highest power of a variable in the whole expression. So, for example, if you have the polynomial 3x to the 7th power, 4x to the 6th power, plus x plus 9, you look at all those exponents. We've got 7, 6, 1. Remember, there's an invisible 1 on that x and o for the constant term. The highest one is 7, so the degree of that entire polynomial is 7.
Makes sense.
Another example, 5y to the 6th power, 4y squared, 6. Highest power of y is 6, so the degree is 6.
Easy peasy.
Oh, and here's a fun little tidbit. The degree of any constant polynomial, like the number 2, is actually 0. Because remember, we can think of 2 as 2 times x to the power of 0.
Sneaky zero, always popping up.
Okay, so just like we categorize polynomials by how many terms they have, we can also categorize them based on their degree.
Right, another way to group them.
A polynomial with degree 1, that's called a linear polynomial, they usually look like this, x plus b, where a can't be 0. Examples include things like 4x plus 5, 2y t plus 2, 3u 2 by 1, 23y plus 1, even just 2u. All linear polynomials.
They're called linear because their graphs are straight lines.
Ah, interesting. So then we have quadratic polynomials. Those have a degree of 2. They generally have this form, x squared plus bx plus c, where a, again, can't be 0. And our sources have a bunch of examples. 2x squared plus 5, 5x squared plus 3x plus p, just x squared by itself, x squared plus 25x, 5y squared, 4y plus 5y squared, 6y squared, all quadratic.
And those graphs are parabolas, you know, those nice symmetrical curves.
Cool. Then we move up to degree 3, and those are called cubic polynomials. The general form is x cubed plus bx squared plus cx plus d, and, you guessed it, a can't be 0. Examples include 4x cubed, 2x cubed plus 1, 5x cubed plus x squared, 6x cubed x, 6x cubed, and 2x cubed plus 4x squared plus 6x plus 7.
Cubic polynomials, they can have some interesting twists and turns in their graphs.
I can imagine. Now, we can actually generalize this pattern. A polynomial in one variable, let's say x, with degree n, it'll have the form an xn plus a plus a1x plus a0. The important thing is it can't be 0.
Right, that's what makes a degree n.
And all those other a's, they're just constant numbers. Oh, and one more thing about degrees. The degree of the 0 polynomial, that's just plain old 0, is actually not defined.
Yeah, that was a bit of a special case.
All right, so we've got all the definitions down. We know all the fancy words. We can categorize these polynomials in all sorts of ways. Now let's get to a really important concept, especially when we're thinking about actually solving polynomial equations. Zeros of a polynomial.
Zeros, yeah, those are crucial.
So a zero of a polynomial, let's say we call our polynomial px, is basically a number, we can call it c, that when you plug it in for x, the whole thing equals 0.
So if P of C equals 0, then AC is a 0 of the polynomial.
Exactly. Our source gives us a nice simple example. The polynomial ps equals x1. If we replace x with 1, we get px equals 1, 1 equals 0. So 1 is a 0 of that polynomial.
Sometimes you might also hear it called a root, like the root of the equation x1 equals 0 is also 1.
Oh, that's right. Now, remember how we said constant polynomials, like 5, they have a degree of 0? Well, they also don't have any zeros.
It makes sense that you think about it.
Right. There's no number you can plug in for x to make 5 equal 0. It's always going to be 5.
Always 5.
But then, on the flip side, we have the 0 polynomial, px equals 0. That one's kind of weird. It's like the opposite of the constant polynomials.
Yeah, it's unique.
By convention, every single real number is considered as 0 of the 0 polynomial. Because no matter what you plug in, it always equals 0.
Always 0.
Our sources give us some more examples to help us really wrap our heads around zeros. Like, they ask, are -2 and 2 zeros of the polynomial x plus 2? So let's check. If we plug in -2 for x, we get -2 plus 2 equals 0. So -2, that's a 0.
It works.
But if we try x equals 2, we get 2 plus 2 equals 4, not 0.
So 2 is not a 0 of that polynomial.
And then they have another example where they ask, How do we find a 0 of the polynomial px equals 2x plus 1? Well, to find a 0, we want the whole thing to equal 0, right?
Exactly. Set it equal to 0 and solve.
So we have the equation 2x plus 1 equals 0. Subtract 1 from both sides, we get 2x equals -1. Then divide by 2, and we get x equals -12. So -12, that's a 0 of the polynomial 2x plus 1.
Boom. Found it.
And there's actually a general rule for this. For any linear polynomial, like x plus b, where a isn't 0, there's always going to be exactly one 0, and you can always find it using the formula -b.
Handy little formula.
Then our source throws in a slightly more complex example. They want us to see if 2 and o'ers are zeros of the polynomial x squared 2x. Let's test it out. If we plug in x equals 2, we get 2 squared 2 times 2, which is 4. 4 equals 0, so 2 works. It's a 0.
Checks out.
And then if we try x equals 0, we get 0 squared 2 times 0, which is 0. 0 equals 0. So 0 is also a 0.
Interesting. So this polynomial has two zeros.
This example brings up some important points. First, a 0 of a polynomial. It doesn't have to be the number 0, like in this case 2 is a 0. And second, the number 0, we can actually be a 0. Like in this example, 0 is a 0. And third, remember how we said every linear polynomial has exactly one 0? Well, this example shows that other polynomials, like this quadratic one, they can have more than one 0.
Right. More complex polynomials can have more zeros.
Okay, so now we're going to touch on something pretty powerful, and it ties together these ideas of zeros and polynomials. The factorization of polynomial.
Factorization, yeah, that's a big one.
And there's this super helpful theorem called the factor theorem.
It's like a shortcut, almost.
Basically, the factor theorem tells us that there's this direct link between the zeros of a polynomial and its factors. It says two things. First, if you find a number, let's call it a, that makes your polynomial px equals 0, so pa equals 0, meaning a is a 0, then you automatically know that xa is a factor of that polynomial.
It's guaranteed.
And second, it works the other way around too. If you know that xa is a factor of p of x, then you know that pa must be equal to 0. It's like a two-way street.
Super helpful for going back and forth between zeros and factors.
Our source gives an example to illustrate this. They ask, is x plus 2 a factor of two different polynomials? X cubed plus 3x squared plus 5x plus 6 and 2x plus 4.
So the first step is to find the 0 of x plus 2.
Right, which is -2. So for that first polynomial, x cubed plus 3x squared plus 5x plus 6, we plug in x equals -2. We get co-cubed plus 3 squared plus 5x plus 6, which, if you work it all out, that equals 0.
So the factor theorem tells us that x plus 2 must be a factor of that polynomial.
Exactly. Now, what about the second polynomial, 2x plus 4? If we plug in x equals -2, we get 2x plus 4 equals -4 plus 4 equals 0. So x plus 2 is also a factor of that one.
Which, you can actually see pretty easily just by factoring out a 2. 2x plus 4 is the same as 2 times x plus 2.
Right, right. The factor theorem is also really useful for finding those missing pieces. Like if you have a polynomial with an unknown coefficient.
Like a puzzle.
They give an example where they say, find the value of k if x1 is a factor of the polynomial 4x cubed plus 3x squared 4x plus k.
Okay, so we know x1 is a factor. That means if we plug in x equals 1, the whole thing should equal 0.
Right, so we get 4x cubed plus 3x squared 4xk equals 0. Simplify that all down, and we get 4 plus 3, 4 plus k equals 0. So k must be -3.
Nice. Solved it.
Our source then briefly mentions how we might factorize quadratic polynomials, which is something you probably learned about in school. It involves this thing called splitting the middle term.
Right, you rewrite that middle term in a clever way so you can factor the whole thing by grouping.
Exactly. And the factor theorem, that can also help us factorize, especially for polynomials with higher degrees. If you can find at least one 0, then you know one of the factors and you can kind of work from there. It's a step-by-step process to break things down.
Makes it more manageable.
Okay, almost done. The last thing we need to talk about, we can't forget about algebraic identities. These are basically equations that are always true, no matter what values you plug in for the variables. You've probably seen some of the famous ones before.
Oh yeah, the classic ones.
Like, we've got the squares, x plus y squared equals x squared plus 2y squared plus y squared, and xy squared equals x squared 2y squared, and of course the difference of squares, x squared y squared equals x plus y xy.
Those are fundamental, for sure.
And there's some other important ones too, like x plus a x plus b equals x squared plus a plus b x plus ab. Then there's the one for squaring a trinomial. X plus y plus z squared equals x squared plus y squared plus z squared plus 2y plus 2yz plus 2zx. And the cubes, x plus y cubed equals x cubed plus y cubed plus 3yzx plus y. And xy cubed equals x plus y cubed 3ayzx.
They can get a little long.
They can, but they're super useful. And there's even one for the sum of 3 cubes. X cubed plus y cubed plus z cubed, 3iyz's equals x plus y plus z, x plus y squared plus z squared, xyzzx.
That one's a mouthful.
It is, but it can be helpful in certain situations. Our source gives some examples of how these identities can actually save you a lot of time, like when you're multiplying or factoring. Like if you need to multiply 105 by 106, instead of doing long multiplication, you can think of them as 100 plus 5 and 100 plus 6, and use that x plus a, x plus b identity to get the answer way faster.
Yeah, they're like shortcuts.
Exactly. And they're also key for factorization. You can recognize patterns and rewrite expressions in a much simpler way. Like if you see 49a squared plus 70a plus 25b squared, that looks complicated.
It does.
But if you recognize that it fits the pattern of x plus y squared, where x is 7a and y is 5b, then you can immediately factor it as 7a plus 5b squared.
Way easier.
Or if you see something like 425y squared, 94x squared, you can use the difference of squares identity to factor it as 25y plus 32x, 25y 32x.
Much cleaner.
And these identities, they're not just limited to expressions with two variables. You can use them for more complex expressions too.
They're powerful tools.
So there you have it. We've covered a lot of ground today. We've talked about what polynomials are, all those key terms, coefficients, degree, and how we can classify them. We've explored zeros and the factor theorem, and we even touched on those important algebraic identities.
It's a good foundation.
It is. And understanding this stuff, it's really the first step towards understanding more advanced algebra and how all of this math actually plays out in the real world.
Yeah, you start to see it everywhere.
It's true. I mean, think about it. As you go about your day, look around and notice those curves, those patterns. And who knows, maybe there's a polynomial behind it all, helping to describe the shape of things, the way things move. Pretty cool, right?
It is.
So keep exploring, keep those math eyes open, and we'll catch you on our next deep dive.